Okay, Assalamu alaikum. Let's start the next session for EEE 6311. And so we are going to start actually with the case number 2. So in the last session, we talked about case number 1, where we actually followed the priority list scheme, strict priority list or strict priority ordering scheme for solving a unit commitment problem. So in case number 2, we will be solving the same problem. However, now we will be following a different scheme, different than the priority list scheme. So in this case, we will be following a scheme which is known as the enumeration scheme. And there are some of the features associated with the enumeration scheme. Feature number 1, now we are not going to follow any priority list scheme. So rather than that, we will be actually allowing all the states to take part in the competition, okay, for getting selected. So this is one of the differences. So in this case, under the enumeration scheme, we are going to choose the feasible states based on the capacity of the combination. Means, let's say if the demand is 500 megawatts, so considering the first feature, so now all states can take part. So all states are allowable. So all states are allowable now. But among those allowable states, which one are the feasible states? So the feasible states must have the capacity to cover the demand, to satisfy the demand. So if, let's say, the demand is 500 megawatts, so if we go for, of course, this table, this list is based on the capacity ordering, remember. So this is the capacity ordering, means that the combination among the units are arranged in such a sequence that if we go from bottom to the top, we will only experience an increment in the maximum net capacity for that combination. So, okay. So if we have a 500 megawatt demand, that means if we look from here, the first state, so you see the maximum possible capacity or maximum net capacity is only 60 megawatts. So, and if you go like this, and then we follow up to this point, so all these states are actually not feasible. And these states will become feasible. And this feasibility is defined or found only based on the net maximum capacity for these combinations. Okay, so here we don't have anything to do with the priority ordering. Okay, so this is the second feature here. The third feature is we don't have the minimum uptime and downtime under consideration. So the minimum uptime and downtime are still ignored. However, in another example, we will actually take care of this part. Okay, we will be considering minimum uptime and downtime, and we will be showing how that affects the calculation of the unit commitment problem. And the feature number 4, which is actually the same. So the feature 3 and 4, these are the same as case 1. So number 4 says that we are still ignoring the hot start cost. That means if anything is mentioned about startup cost, that would mean it is a cold start cost and not the hot start cost. Okay, so these are the features. So keeping all these in mind, so now we know that we have the load variation or the hourly load variation for an 8-hour period already given. We know the unit characteristics, the unit cost functions or unit heat rate curves, incremental cost curve or incremental rate calculation. Everything is done beforehand like case 1. So all the previous calculations are still valid. By the previous calculation, what I mean is this. So the preliminary calculation shown in slide number 38 still applies. The priority ordering shown in slide 39, it doesn't apply anymore. The calculation here for case number. So this is the starting of case number 1. So we are not going to take this anymore. However, the unit characteristics are still represented by the simplified version, the straight line characteristics, that is the straight line relationship, like y equals mx plus c. So if this is our y, this is the c, the constant, and this is m, and this is multiplied by x. So f is the function y, and p is our x, m is the slope, which is the incremental cost. So this one still applies. The load variation remains the same. So if we go for the load variation again, this is the same load pattern shown in slide 32. The same initial status and startup cost table still applies. Slide 31, slide 30, unit description, all these are still applicable. Okay. So keeping all these in mind, now let us go to case number 2, calculation steps. Slide number 40. So start with our number 1. The initial condition is as mentioned earlier, so that is state 12, and that means the combination is 0 1 1 0 among unit 1 2 3 and 4. Means initially our unit number 2 and unit number 3 are in operation, unit number 1 and unit number 4 are out of operation. So now, as we said that, well, the demand is 450 for our number 1. If we check back at the capacity ordering, so we see that, well, from state 11 up to state 1, they can only produce a maximum of 440 up to state number 11, which is not sufficient to satisfy 450 megawatts. So the feasible states will be 12, 13, 14, and 15. These 4 states are feasible states. So those are listed or included within the set X, and these feasible states are determined based on the capacity. Now let's go into the table. So table is formulated as, in the identical manner as we showed for case number 1. So these are my initial status L taken from here, and these are my elements from X. So each element in X, I am calling them as I. Okay. So let's start from here, from the bottom. So the demand is 450. So unit 2 and 3 are currently running. So if we try to switch from 12 to 12, we are going to have the same combination. Unit 2 and unit 3 are going to be turned on. The demand is 450. So the lowest cost unit is unit number 3. So we fill it up. We take the maximum out of it, that is 300 taken from the given data, and the remaining 150 will be taken from unit number 2. So combinedly they will give us 450. The cost was actually calculated earlier, so the same way we can calculate the production cost, the P cost. The transition cost, because we are not having any transition between the states, so the transition cost will be 0. Again, the F cost K minus 1, this refers to the initial, basically the cost at state, or the cost at hour number 0. So we actually haven't any stored value there. So we will assume them to be 0 for all the I values. Okay. So at this stage, hour number K equals to 1. For K minus 1 means it is the initial status, and we don't have any information regarding that. So we assume them to be 0. So then we calculate the F cost Ki. So simply you add up 9208 plus 0. So it remains as 9208. We do the same for the next one. So between 12 and 13, that is the next one, between 12 and 13. 13 means you have a 0, 1, 1, 1. If you go to the capacity ordering, 13 means 0, 1, 0, 1, 1, and 1. Okay. So the first unit is off, the remaining 3 units are on. So again, we start with the lowest cost unit, and that is unit number 3. We take the maximum out of it, 300. Remaining is 150. So we have to run unit number 4. So because it is the highest cost among these 3 units. So we'll pick the minimum out of it. So that means this is 20. So now we have to go to number 4 data. Just a minute. So for unit number 4, the minimum is 20. So we can take 20. So if I take 20, then it makes it 320. So what I'm saying is I'm taking from unit 3, 300 megawatt. Unit 4, I'm taking 20 megawatts. My demand is 450. So the remaining is 130. So another unit to be run is unit number 2, because the combination is 0, 1, 1, 1. Unit 1 will give 0. So unit number 2, the remaining should be taken from unit number 2, which is 130. So combinedly, they should give 450. So now the question is it okay for unit number 2? Let's check. Yeah, it is okay. It is within 250 and 60. It is within the limits or within the bounds of unit number 2, that is 130. So that combination is fine. So we can proceed with that. So let's go to that slide, which is here. Okay. So that is 130 for unit number 2, 300 for unit number 3, 20 for unit number 4. You should be able to calculate the production cost for this combination, 130, 320. Now the transition cost, what is the transition? Okay, let's see what is the transition. So transition says you were at 12. So this is 12 and you are jumping to 13. And this is 13, 0, 1, 1, 1. So the only bit that is changed means this one, and that is turning on, okay, starting up unit number 4. So what is the startup cost for unit number 4? Let's go and check. What is the startup cost? The startup cost for unit number 4 is 0, whether it is cold or hot. However, remember that for this problem, case number 2, we are still considering cold start cost. So that is 0. Okay, so for this transition, we don't have any cost. Okay, so so the value of startup cost here remains at 0. So simply add this 9576 with 0. So you will get 9576. Then from 12 to 14, 14 is 1110. So you see 1110. So again, you take the maximum from the lowest cost unit, that is 300. Then you jump to the highest cost unit among these 3, that is unit number 1. So you take the minimum from that, and the remaining you take from unit number 2. You calculate the cost. What is the transition from 12 to 14? So 12 is 0110, 0110. This is 12. This is 14. So now there is a change of bit in unit number 1. So what is the startup cost for unit 1? Let's check. The startup cost for unit number 1 is 350. Remember the cold start cost. So 350 is the startup cost for unit number 1. So you see here we have the 350 for the transition from 12 to 14. So now you add this and this and you get this. Similarly, you do the same. Similarly, you do for this transition from 12 to 15. So now all the units are on. So you pick the lowest one first, the lowest cost unit, you load it to the maximum 300. Then the highest cost unit, you pick the minimum, that is 20. The next highest cost, you pick the minimum, that is 25. And the remaining should be taken from unit number 2. But you have to check again whether this 105 is within the bounds or not for unit number 2. So let's check it. For unit 2, yeah, it is 105 we are taking. So it is between 250 and 60. So that is good enough. So you pick this value for our number 1. So this is the combination now, 25, 105, 320. This is the production cost, the transition cost. Now 15 means you are jumping from 12 to 15. So this is 12 and 15 is this one, 1, 1, 1, and 1. However, we know that there is no startup cost for unit number 4, but there is some startup cost for unit number 1, and that is 350. So that is included here. Now you add up this, and that should give you this. So now you compare all these, you find the minimum one is for this transition from 12 at hour 0 to 12 at hour 1. Okay, so this is the minimum one, and now you again choose to save the 2 least cost states or 2 least cost strategies. So this is the winner and this is the second one. So you choose 12 and 13 and 12. So the progress is, so hour 0 it was 12, hour 1 it is still 12. So this is k equals to 0, that was given actually. This is k equals to 1. So 12 is the winner. Now we do the same thing. We apply the same sort of steps for the hour number 2 with a different demand. Okay, so of course the demand would be increased. Probably it is 550. Okay, so let's see. So in the next hour, k becomes 2. These n values, they become L. They become the elements of the set L. Okay. Now let's go to hour number 2. So the load has increased to 530. So what are the states that are feasible? Again, 530. So let's go back and check the capacity ordering. So 530 means still 12, 13, 14, and 15. Only these 4 are possible. So these 4 are feasible because the demand is 530. So 440 is not enough. So 12, 13, 14, and 15. These are the feasible states still. So the feasible states are listed within X. The previously saved states, which was the elements of capital N previously, now they become capital L at hour number 2. So L is 12 and 13, previously saved states. So you see L is now 12 and 13, 12 and 13, 12 and 13, 12 and 13. From each of these, there could be a jump from any of this. There could be a jump from here up to here. Okay, from 12 to 12, 12 to 13, 12 to 14, 12 to 15. Similarly, from 13 to 12, 13 to 13, and so on. So all those combinations are listed here. Now, if I jump from 13 to okay, let's start from here. From 12. Okay, from 13 to 12. From 13 to 12. From 12 to 12, there is no transition cost. Okay. From 13 to 12, I'm going to 12. So 12 means 0, 1, 1, 0, 0, 1, 1, 0. So the demand is 530. Take the maximum for the lowest cost unit, that is unit number 3, and the remaining peak, the remaining value for the demand should be taken from the remaining unit. So that is unit number 2. Pretty straightforward. 300 and 230. This is the load division among the units. Calculate the cost. This is the production cost at this hour k, and for this I value. Okay, 10,648. The unit transition from 13 to 12. The 13 is 0,111. 12 is 0,110. So where is the change? The change is only in bit number 4. Okay, the 4th bit, that is unit number 4. But there is no shutdown cost. This is actually shutting down. Okay, this is not starting up. This is rather shutting down. So the shutdown costs are actually ignored altogether. So you don't have to bother about it. That's why the transition cost is 0 here. Okay, the F cost column has to be taken from the previous slide. So that F cost will actually come from here. Okay, 9208, 9576, 9843, 10211. Okay, so sorry. So among those, actually, sorry, not all these. Actually, we are saving the least two least cost strategies. So 9208 and 9576. Only these 2 will come. 9208, 9576. So 12 and 13, 12 and 13, 12 and 13. These 2 are the saved states. So those corresponding F costs will be listed here. Okay, so only these 2 will become available. So you add up 230, 300, 10,600. Sorry, you'd add up P cost, S cost, and F cost. So add up these, and these, and this. So you see, if you add the top one, that would be higher than the bottom one. That means if we follow this pattern, you reach here. If you follow this, you reach to some value. You compare these two, and you leave with the lowest cost among these two. Okay, that is the dynamic programming algorithm. Stay with the lower cost, because of course the target is to minimize the overall cost. Okay, that is our target. That's why we are inclined towards the lower costs every time. So we do the same for this one. From 13 to 13, there is no transition. From 12 to 13, whatever transition is there, that is starting up of unit number 4, but it doesn't have any cost. The startup cost for unit 4 is 0. So you see 0 here. There is no transition because it's from 13 to 13. And similarly, we calculate the P cost for this combination of 13. So the demand is 530. You take 300 from unit 3. You pick the minimum from the highest cost unit 20, and you pick the remaining from the remaining unit 210. Calculate P cost, get the S cost, take the F cost from the previous step, and you add up, and you compare this one and this one, and you will see that this one is the lower one. So I'm staying with the lower one. I'm only storing the lower value. And similarly, you calculate for the other 4 combinations, and you get 2 more values here. So in total, you have 4 values under the F cost column. And again, you see the winner is 12. So the progress would be 12. You store the 2 least cost strategies. So 2 least cost strategies is 13 and 12. So again, 12 and 13 are stored within N. Go to our number 3. The demand is further increased. Now, because of this increment, another state has been taken out of the feasible states. That is a state number 12. Okay, because a state number 12 can only provide how much? State 12 can only provide 550. However, the demand has now become 600. So the feasible states are only now state number 13, 14, and 15. The previously saved states are 12 and 13. We are at our number 3. So there will be transition from 12 to 13, 12 to 14, 12 to 15, and 13 to 13, 13 to 14, 13 to 15. Okay. And I think you can now follow the steps. You should be able to solve these things. Okay. Same thing, same way we do the calculation. You know now how to calculate the transition cost. The only thing that you have to remember, there is no shutdown costs. Okay, the shutdown costs are neglected for this example. No shutdown cost. So for shutting down of any of the units, there will be no state transition cost. That thing has to be kept in your mind. Okay, so again, you calculate P cost, you bring the F cost from the previous slide, and you calculate F cost, which should be the minimum among these two, minimum among these two, and minimum among these two. Now you again stored the 2 least cost strategies. So now you see the progress has now changed. We are no more at state 12, rather we are going to state 13, because state 12 is actually no more a feasible state. So we can't stay at that. We have to change our track. So from 12, we are actually jumping to 13. And accordingly, the cost is 32,306. This is the least cost. And 2 least cost strategies are also updated. It is no more 12 and 13, rather it is now 13 and 14. So this is our number 3. Now we continue in the same manner to our number 4. The demand, let's check the demand. What is happening with the demand? Okay, the demand has decreased. Now it is less than 550. So the unit 12 again comes into play. Okay, so now the previously saved states are 13 and 14. Now there will be transition between all these. So there will be 8 possible transitions. So that 8 possible transitions are listed in the first 2 columns. These are the unit productions. This is your P cost. You calculate the P cost. This is the transition. F cost you pick from the previous slide. F cost K minus 1L, and F cost Ki is actually, you have to calculate and compare the 2 possible combinations. Okay, So you compare this plus this plus this, which gives you this, and also this plus this plus this, which would give you something here. You compare these two, and you would find that this is the lower one. Similarly, you add this, and this, you get this. You add this, and this, you get something here. And you compare these two, and you should find that this is the minimum among these two. And you do the same for this one and this one. After comparison, you get this one and this one. Still, this is the lowest cost, and this is the second lowest cost. So you store these two, 12 and 13. Now the winner is 12 because it is providing the lowest cost. So now the progress has again changed from 13 to 12. The currently saved states are again updated. This is 12 and 13. 12 and 13. Let us go to hour number 5. So of course the load would be updated, the load magnitude. So let's check the load magnitude. Okay, it is reduced to 400. The previously saved state at 12 and 13. Now the feasible state has increased. Okay, number 11 state is also now, you see, 440 it can produce. The demand is 400. So state 11 will now come into play. It will also take part in the competition. Previously saved state are taken from the previous slide, 12 and 13. So now there will be 10 different transitions, possible transitions. Okay, all those are listed here. The corresponding unit productions are here. This is the P cost, the S cost, the transition cost, the F cost taken from the previous slide, and F cost K here, KI is calculated. So now you see the transition is still with this from 12 to 12. So this one is the minimum highlighted by color red text. And the two minimum costs are again 12 and 13. This is for 12 and this is for 13. So again, we save these two, 12 and 13. The progress is like this up to hour 5. Let's go to hour 6. The load demand has decreased further, okay, further reduced, pretty much reduced, 280 megawatts. Well, due to that, what do we have? We see that suddenly the number of feasible states has increased because we are actually allowing all the states to take part. All the states are allowable states, unlike the priority list ordering. So all the feasible states now, how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Well, 11 feasible states and 2 previous states. So there will be actually 22 different combinations. That's a huge amount of calculation. That is of course not shown here. Okay, that is not shown here because of space constraints, but you can do on your own, of course, because you know the logic now. So you do it on your own, and you should find that at this stage, at that hour k equals to 6, the progress should be from 12 to 5. Okay, up to 12 was up to hour k equals to 5. Now at hour 6, state number 5 will be the winner. Okay, and then hour 7, the load has changed a little bit, 290. Still we have 11 feasible states, and L should come from the previous hour. Okay, should come from the previous hour. So still you save the 2 least cost strategies and proceed to the next hour. Now the winner should be also 5. The answer is given here, not the calculation, remember. Hour number 8, the last one, 500 megawatt. Okay, because of the increment in the load value, the feasible states are now reduced, only 4. Again, you pick L from the previous hour. You calculate the transitions and everything for all the combinations here. Calculate the F cost, and finally you should get this one. This is your final result. So this should be your strategy. 12, 12, 13, 12, then 12 again, then 5, 5, and 12, which is of course different than what we got for priority list ordering. Okay, for priority list ordering, what did we get? For priority list ordering, our solution was something like this. Okay, it was 12, So mostly it was 12, 12, then 14, then again 12, 12, 5, 5, and 12. Okay. However, for this one, so you don't see state 13 here. Okay, you don't see state 13 here. However, here you see we have the presence of state 13. Okay, 12, 12, 13, 12, 12, 5, 5, and 12. So it is of course a little different than the priority list ordering scheme. So based on your scheme that we are considering, based on the scheme that we are considering, actually the progress of the solution will become different. And the amount of calculation will also differ. Okay. So now that's the end for case number 2. Remember, if you remember clearly, I talked about 3 cases, but case 3 will take a lot more calculations because case 3 takes into account some more constraints. Okay. So case 3 tells us that, well, in case 3, you follow the enumeration scheme like case 2. Now you consider uptime and downtime. You also consider the hot start costs. So there will be few more complexities introduced due to all these relaxations. Okay, means due to all these considerations actually. So you consider minimum uptime and downtime of each of the units. So you cannot actually turn on or turn off any units, I mean immediately. Okay, immediately you cannot do that. You have to wait until this minimum uptime or minimum downtime has been elapsed. So, and also you have to consider the hot start cost. In case 1 and 2, we only considered the cold start costs. Okay, so the calculation steps will be a little different. So I'm not taking this example here. So I hope you can go through it and you can have a crack at that. Okay, for case number 3. So another example, actually a small example, I should say, considering the number of units involved. Actually, this example gives us the idea about the minimum uptime and downtime constraints. Okay, so specifically we will be focusing on these 2, minimum uptime and minimum downtime. So this example helps us to get the idea of calculation steps, where the minimum uptime and minimum downtime are involved, both are involved. Here we have the data for 3 units, A, B, and C. Also for all the 3 units, we have the minimum and maximum. Of course, these values are given. The uptime and downtimes are given in hours. The no load costs, there are no load costs. Okay, so it is completely the cost F is simply, if I write down the previous formula for the previous example, no load cost plus incremental cost or marginal cost, all the same, multiplied by P. Okay, that is the production. So here the no load cost is 0 for all the units. So that means your F of P is simply the marginal cost or incremental cost, all the same, multiplied by the production. So if you know how much production you are going to make or how much production each of your units is going to make, then if you know the marginal cost, you simply multiply with that, and that should give you the cost function, that is the production cost. Okay, fuel cost function. This is the fuel cost function, simply straight line through the origin. So you can say straight line through the origin here. There is no interception here. So it is, we can say y equals mx instead of y equals mx plus c. Okay, so startup costs are given directly, so you don't have to bother about hot start or cold start. And the initial status is given. So initially there is given that if I say A, B, C, so initially the initial status is something like 1, 0, 0. So this is the initial unit status. Okay, so these are the data given for solving the problem. Okay, so now let us see what is the load profile. Okay, we have to know what is the load profile and how long we have to, for how long we have to solve this problem. So if you look at the cost curves, as I said, these are actually all straight line through the origins. So for unit A, the slope is the lowest. For unit B, there is intermediate slope. For unit C, the slope is the highest. If we check, you can see the marginal cost for unit A is the lowest slope, unit B, intermediate slope, and unit C, the highest slope. Okay, so that is reflected in this diagram by the straight lines through the origins. What about the load demand? So we only have to solve for 3 hours. So that's why I said it's a small example. And the demands are like 150 at hour 1, 300. The load jumps up to 300 units. And then at hour number 3, it comes down to 200. Okay, so this is the load variation. What are the feasible unit combinations? The feasible unit combinations, we are actually taking this problem, solving this problem in a little bit different manner. You can say we are taking help of more like graphical approach, okay, rather than calculation. We are putting all the information with the help of some nodes. Okay, so these nodes, we see how many nodes are there: 1, 2, 3, 4, 5, 6, 7, 8. These all these nodes corresponds to the states. Okay, so for our number 1, there are 8 states. For our number 2, there are again 8 states. For our number 3, there are again 8 states. So these are actually our number 1, 2, and 3. And these values are actually the demands: 150, 300, and 200. How we are actually drawing the feasible units? So the highlighted blue ones, okay, the filled up blocks, the filled up circles are actually the feasible combinations. How we are actually getting the feasible combination? Let's see. Okay, so if the demand is 150, okay, before that, let's come to this. So this is basically not capacity ordering. This is simply the binary ordering, but of course you can go for capacity ordering. Okay, but here the binary ordering is shown. So it is 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on. So there will be 2 to the power 3 up. That means 8 possible combinations. Among these, actually, this is always infeasible because it doesn't actually give you anything. Okay, there is no Pmin, there is no Pmax. So that's to say we only have 7 possible states. If we leave out this last one, then 001 means unit C is operating. What is the value for unit C? 10 and 50. So you see 10 is the minimum, 50 is the maximum. For this one, 010, unit B is operating alone. So unit B operating alone. So 50 and 100. 50 and 100 and so on. If B and C both are operating, so you add up the minimums, 50 plus 10, so it is 60. 100 plus 50, it is 150. When unit A is only operating, so you go to the data, 150 and 250. So 150, 250. When A and C are operating, so you look at the C value and look at the A value. So 150 plus 10, 160, and 250 plus 50, it is 300. So in this manner, we can complete the table. Once we complete the table, now let's see 150. Which of the states can satisfy this demand? So if we see this one cannot satisfy, this one cannot satisfy, this one can satisfy because we can pick the maximum out of it, and this one also satisfies because the minimum that we can pick. If we go beyond this, that would mean, well, from this combination I can only, okay, so 150, actually you see the demand is 150, but the minimum that I have to generate is 160. So that means if I choose this unit, I am already losing at least 10 megawatt. Okay, so 10 megawatt becomes useless, or 10 units of power becomes useless if I choose anything here. It is the least, and the maximum that I will lose is this much. If I choose this one, the minimum that I will lose is 50 megawatt because the demand is only 150, 50 megawatt or 50 unit, whatever. If I choose this, I'm going to lose 60 unit of power at least. So that's why we are only choosing this one, where this is the maximum, which equals the demand, and this is 150, which is the minimum that satisfies the demand. So only these two becomes the feasible states there. So as I said, we are actually thinking it a little bit differently, not like the previous one. In hour number 2, at hour number 2, the demand increases 300. So we apply the same thing. So up to this, it's not possible to satisfy 300 megawatt. This is possible. And here I can pick anything between these two. So that is possible. And here it is also possible. I can pick 300 among these two ranges. Okay. So thus these three states, this state, this is in this state, they are the feasible state at hour number 2. At hour number 3, the demand again falls from 300 to 200. So because it is 200, we shouldn't pick this. Okay, because it is the minimum is 210. So that means we will be losing at least 10 unit of power. So we don't want that. Here it is between 200 and 350. So 200 is the demand. So we can do with 200. It is between 200 and 200 and 350. This can be chosen. This could be chosen. Also, this could be chosen. Nothing else. Nothing else could be chosen. So this, and this. So that means this, and this could be chosen as the feasible states for our number 3. Okay. So after that, once we have chosen all the feasible states, so the next step, let's go to the next step. Now, among these feasible states, we may have the transitions. Okay. So we have only listed the feasible states here, feasible at any of the 3 hours, okay, any of the 3 hours. So combinedly 1, 2, 3, 4, 5, only 5 states become feasible states. Okay, the remaining 3 among the 8, the remaining 3 are never feasible in these 3 hours. So we just drop them from the list. What is the initial state? Initial state, in the initial state, it was 100. That means unit A was only turned on. So you see 100, this is the initial state. This is the initial state represented by the purple node. Then at hour number 1, we had these two feasible states. Remember 100 and 011. If we check back, so you see 100 and 011. These are the feasible states. So 100 and 011. Similarly, at hour number 2, there were 3, 111, 110, and 101. So you see 111, 110, and 101. So these are the 3, 111, 110, and 101. Similarly for hour number 3. And the transition is possible. Actually, we may have some transitions between any of the nodes, between any of the 2 nodes, or any of the 2 nodes at consecutive hours. So from the initial state, you may go from here to here or from here to here. Similarly, from hour 1 to 2, you can have jump from 1 to 2 here, 1 to 2 here, or 1 to 2 here. And similar thing can happen between any 2 other nodes. So that is a possibility. Now, whether it is feasible, we have to check. Okay. So for feasibility, we will now take into account of the 2 minimum times. Okay. One is the minimum downtime. Another one is the minimum uptime. Okay. And thus we will be finding out some infeasible transitions in this slide. So now let's start with the minimum downtime of unit number A. Okay, so these are the minimum downtimes, TD. So this column is the minimum downtime for each of the units. This column is the minimum uptime for each of the units, TD and TU respectively. So from initial state, as we said, we can have some jumps here and there. And then we see, well, if I have to have a transition from hour number 1 to hour number 2, from here to there, so this from here to here, is it feasible? Okay, we are actually looking for some infeasible. So let's find out the infeasible ones, which are actually shown by the dotted lines. So we start from here. That is the infeasible one. Why it is infeasible? Because of the minimum downtime of unit A. So let's check. Remember, the minimum downtime for unit A is 3 hours. So if I jump from here to there, what is the transition? I was actually at 011. So this is 0, 1, 1, and I'm jumping to here, which is 1, 1, 1. So you see, the unit A was off here, and it has to be turned on within 1 hour. Within 1 hour. Remember, these are the hours. So within 1 hour, I have to turn on unit A. But my minimum downtime is 3 hours. So I cannot do that. Well, I cannot do that. So that's why this is infeasible transition. Let's check this one. It is 0, 1, 1. What is this one? 1, 1, 0. Okay, so this is 1, 1, 0. Again, I have a transition from 0 to 1. So I cannot do that within 1 hour. Okay, so this is another infeasible transition from hour 1 to hour 2. Next one, from here to here. What is this one? 101. So this is 101. Again, you see, unit A was off at hour 1, and I cannot turn it on immediately in the next hour. Okay, I have to wait for 3 hours before I can turn on unit number A again. And this is the constraint imposed by the minimum downtime for unit A. So these 3 transitions are not feasible due to the minimum downtime of unit A. Okay. Similarly, there are some other infeasible transitions that we can find. And now that is associated with the minimum uptime of unit B. So now we are looking at the minimum uptime of unit B. So this is the value, 2 hours. That means once unit B is turned on, you have to wait for 2 hours, 2 more hours to turn it off again. Okay, once it is turned on, you have to wait for 2 hours to be allowed to be able to turn it off once again. Okay, so let's check. So these are the infeasible transitions, again shown by the dotted arrows or the dotted lines. So this is one of them. So let's write it down. What is this? 1, 1, 1. So this is 1, 1, 1 means unit B is on. Unit B is on here at the middle. What is this? This is 1, 0, 1. So you see, unit B was turned on, and then it is asking to turn off unit B within 1 hour from hour 2 to 3. So this transition from 1 to 0 is not allowed. It's not feasible. Next thing, from 1, 1, 1 to what is this? 1, 0, 0. This is 1, 0, 0. Again, from 1 to 0, transition is not possible within 1 hour. And you can, in this manner, actually, you can check all the other infeasible states. Okay. So if we get rid of all these infeasible states, if we get rid of, okay, what else we have actually done before here, we can see there's an interesting observation. You see, due to the minimum downtime constraint of unit A, all these transitions from the lower node, from 0, 1, 1, this state, all these further transitions from this lower node are infeasible. Okay, so that means it becomes an isolated node. Okay, it becomes an isolated node. So we haven't shown those actually. Those dotted lines are actually removed from this diagram. So you don't see any transition, any possible transitions from here. And now you will see, okay, we will also get rid of all these dashed lines. And then when we move to this slide, you see this node becomes a dead node. Okay, the transition from here to here cannot be actually continued. So we can say this is a dead node. Okay, there is no point of continuing with that node. Okay. So with that, when we get rid of all these dashed lines, we are left with only this feasible transition line, solid lines. Okay. Now we have to calculate the costs for each of the paths. So let's now put down the cost values. Before that, let's put some node numbers here. We start from here, node number 1, 2, 3, 4, 5, 6, and 7, just to just for the ease of our calculation. Okay, nothing else. We give some node numbers, And we now decide on the economic dispatch. We now look into the economic dispatch for each of the nodes. There are 7 nodes, 7 nodes finally remaining in the calculation of the operating costs. So 7 nodes, 1 up to 7. Node number 1, what is the load? Node number 1 can satisfy 150. Remember unit number A, 100. It was satisfying, let's go back, 100, 100, it is satisfying 150. Remember the demand was 150. So the load demand for node number 1 is actually 150. So 150, we only have a single unit available. So that value has to be generated from that single unit, and you can calculate the cost. So your generation is 150. What is the marginal cost? Should be 10. Marginal cost is 10. So 150 multiplied by 10. So that gives you 1500. So this is the 1500. Okay. Node number 2, the load is 300. So let's go to node number 2. Where is the node number 2? Node number 2 is 101. So this is our number 2. Remember, 2, 3, and 4, they belong to our number 2. The node 1 belongs to our number 1. So the load for node number 1 is 150. The load or the demand for all these nodes at our number 2 is 300. And the load for all these 3 nodes, 5, 6, and 7, lying at our number 3 are 200. So you see 300, 300, 300 for nodes 2, 3, and 4, and 200 all up to the node number 7 here, 5, 6, and 7, all for all these 3. The load is the same, that is 200 units. So when it is node number 2, the load is 300. Which units are available at node 2? Let's see, 101. So unit A and C. So unit A and C. Unit A has the lowest cost. You see the lowest cost. So I will try to fill up whatever I have from unit A. Let's see what is the maximum. Yeah, P max, it is the 250. I can take 250 because the remaining 50 is the maximum for the remaining unit C. So if I add the maximum of unit A and the maximum of unit C, I can fill up, I can satisfy the demand. So then 250 into 10 plus 50 into 20. So that gives you 3500. And accordingly, I think you can now calculate all the remaining values over here. Okay, it's pretty easy. So then after we do that economic dispatch, small economic dispatch calculation, we end up with all these costs. Remember, these are the production costs. Okay, all these are the production costs. So all these costs are actually associated with each of these nodes. Okay, for node 1 it is 1500, node 2 it is 3500, and so on. And we pick all these values from this list. Actually all these values are actually pasted here across each of these 7 nodes. So we know what is the production cost for each of these nodes. This is only the production cost. What about the startup cost? Startup costs are given as this, and these are fixed. There is no, I mean, these are not dependent on the amount of time the units are shut down or running, whatever. So the fixed startup costs are given: 1000 for unit A, 600 for unit B, and 100 for unit C. So let's now put these values. Okay, so from initial status was 100. We are remaining at 100. So we are not actually starting any new units for this transition from initial status to node number 1. That's why the startup cost here is 0. Okay. Next, what we have to do, let's check from 1 to 4. Okay, if I jump from 1 to 4, how many units, or which are the units that are turned on? You see 100. So unit B and C were off. If I jump from here to there, then 1 and 1. So unit B and C are turned on. So these 2 startup costs has to be added, 600 and 100. So that's why you see the summed up startup cost, which is 700 here. Okay, because from 100 I'm jumping to 111. So unit B and unit C are turned on. So 2 units are turned on. So these 2 unit startup costs are to be added here. When I jump from here to here, this was 100. I have 110. So I'm only starting unit B, which is 600. So I'm putting it here. When I'm jumping from here to here, I'm changing only the status of unit C, which is only $100. So you see only $100. So in this manner, these and these are done. And similarly, you can see all these values over here. Okay. For example, if I jump from here to here, I'm at 111, node number 4. If I jump from 4 to 7, I'm moving to 110. So I have to shut down unit C, but there is no shutdown cost. So that's why this cost is 0. Okay. So in this manner, I am putting the cost for all these links. Initially, I included the cost for all the nodes. Now I'm including the cost for all the links. Then in the next slide, what we do, we calculate the accumulated cost, which are shown in this pink color. So startup costs are shown in the purple color or the blue color. The black ones are the operating cost or the production cost. Now we will be calculating the accumulated cost. So what is the accumulated costs? The accumulated costs are calculated in this manner: 0 plus 1500. So the cost of the link plus the cost of the node, you add them up and you are left with this. Okay. Then when you reach at this point, what is the cost? What is the accumulated cost at this node? You add this node cost, accumulated cost 1500 plus the link cost to reach there. So 1500 plus 700 is 2200 plus the nodal cost. The nodal cost is 3200. So it adds up to 5400. Similarly, you do it here: 1500 plus 600, it is 2100 plus 3100. So it is 5200. So it is 5400, it is 5200. You do the same here, and that gives you 1500 plus 100, it is 1600 plus 3500, it goes to 5100. So for these 3 nodes, you have the accumulated costs 5400, 5200, and 5100. You do the same here. So 5400 plus 2. Okay. So now what you do? This 7300, this 7300 is basically not the accumulated cost following this path. Okay. So these 2 paths, now you see they are again shown by dotted lines. Means if you calculate this cost, how much it is? Let's calculate it. So 5400 plus 0 plus 2100. So how much is it? Remember, 2100 is the nodal cost here. So if I follow this path, so how much is it? 5400 plus this is 0 plus 2100. So this is 0 0 5 7500. So here I have 7500 for this dotted line. How much is this? 5100. So means this. Okay. So how much is this? 5100 plus 600. This is the 600 plus 2100. So it is 5100 plus 2700. Then it is 0 0 7 and 1 8. This is 7800. So this is basically 7800. Means you have 7500 coming along this path. You have 7800 coming along this path, and you have 7300 coming along this path. 5200 plus 0 plus 2100. So that is 7300. And we only keep the minimum cost. So there are 3 alternate paths to reach at node number 7. We only choose the minimum one, which is this one. Which is this one. So this 7300 is basically the path, the cost, accumulated cost, if we follow this trajectory, this strategy. That is 7300. Okay. That's why you see only one value written there. And the 2 higher costs, search paths or to higher cost trajectories are actually shown by dotted lines. The 7300 is the one followed in this manner. Okay, from initial status to 1, from 1 to 3, from 3 to 7. Okay, what about this one? Okay, so this one is 5100 plus 0 plus 2100. There is only one path, so you keep it 7200. Again, there is only one path, so there are no alternate paths for reaching this node. So it is 5100 plus 2100, that is 7100. So which is the minimum? This one is the minimum among these three. Okay, we have 7300, 7200, 7100. So this one is the minimum. So the search path should be finally, just a minute, let me erase. So this is the lowest total cost. Okay, and the search path would be this one. So for the 3 hours, I have to follow this unit commitment path to yield the minimum cost strategy for the 3-hour operation for the given 3 units. So this is the pattern shown over here. So from initial status to 1, 1 to 2, 2 to 5. So 1 to 5, this is the progress here. Okay, and that's probably the end of the unit commitment lecture. However, there are some comments like the last example that we have shown. It is a pretty much a simplified version, but the target for the last example was not to be too involved in the complexity of the unit commitment calculation. The most complex one is, of course, the case number 3 for the previous example, which is not shown, and I hope you have a crack at that. This last example is basically just to show how actually the minimum uptime and the minimum downtime might affect your feasibility of the states. Okay, and some constraints we have intentionally ignored here. Some constraints are ignored and some are simplified, like we are only considering a fixed startup cost, our production cost, or actually the fuel cost or the operational cost function is also simplified. Okay, y equals mx. We have just done it just to make it, just to help ourselves to solve this problem by hand calculation. Okay, and thus it doesn't actually illustrate the complexity, the actual complexity of the unit commitment problem. The solution method used, of course, it is another way to apply the dynamic programming, because you remember we were always, whenever we found any alternate paths, then we always stick with the lowest cost strategy. Okay, but this technique, that is the dynamic programming technique, it works well for small system. Okay, for any units which is less, well, for any power station where we have less than 20 units. So as you have seen, only for 4 units there are, you might have many transitions possible. Okay, so a huge amount of calculation will be there if the number of units increases. So accordingly, there are more practical ways nowadays, as mentioned at the beginning part of the lecture. Like as I said, different solution methods are available for unit commitment problem. Okay, so like we have taken only 2 actually, like we have shown the priority list ordering, and we have shown the dynamic programming problem. Okay, so the Lagrange relaxation and the mixed integer linear programming, these are not actually taken into consideration. Okay, so I hope you go through the lectures, and if you have any queries, then we can discuss about those in the next class, inshallah. Okay, so till then, have a good day, stay safe. Assalamu alaikum wa rahmatullah.